All right, so let us talk about syntactic extensions of word embeddings, or embeddings that are more syntactically oriented. So what is the basic problem of word2vec? We have seen that just a couple of slides before. Word2vec does not have a notion of order, but we all know that it can make a big difference whether the sentence says a dog bites a man or the man bites a dog. So, and the problem is that word2vec has no distinction between left and right context, and maybe to a lesser degree also between close and far context, even though I think they built something into the model that like downweights contexts that are further away. But for the order, it basically, the basic principle is that if you want to predict from bytes the surrounding context, then in both cases you have tuple of the form byte man or bytes man and bytes dog, and no matter what the order is, you'll always have the same updating procedure. So what we intuitively we want instead is we would like to index the words to mark that in one case dog precedes bytes and in another case dog succeeds bytes, right? So that's intuitively what we want, although in reality we would not implement a model like this. Why would we not implement a model like this? Because we destroy the word identity by prefixing some integers to the words or suffixing some integers to the words. We would destroy the information about the word identity. So dog -1 is not the same as dog +1, and it is neither the same as dog. So what instead people have come up with, like in this paper here, which is from a 2015 ACL paper, I think, what they changed is, this is the original word2vec model where we have the center word which gets embedded, and from the embeddings the context words are predicted. So that's the skipgram model, and we already said previously that such a model cannot distinguish between what is predicted in any of the outputs, because the embedding matrix V is always the same. So what they do instead in this paper is they make new embedding matrices for each context. So, and with these new embedding matrices here, then the whole model changes, because if we do an update, if the update goes over this path here, then once we do the gradient descent and the backpropagation, then the backpropagation depends on the next layer. So the updates here for the embedding matrix are different than when we route it over this path here, for example, then because here we have another matrix, so the updates for the embedding matrix are also different. So the word embeddings that result as a result of this new model are different than those embedding matrices E that result when we have the original word2vec model with only V, with one common V on all of the arrows here. And in particular, if the model is evaluated, then we can check the nearest neighbor of a word such as breaking. And if we go for the original skipgram model, we find that the nearest neighbors are words like breaks, turning, broke, break. So it's all kinds of grammatical forms. So here this is a gerund. This is third person. This is also a gerund of another word. This is past. This is infinitive, and this is again past of a different lemma form. While if we do the structured skipgram models, the thing that we note is, well, all these words end with ing, and this on the other hand means that these are all gerunds. So what we find is these words here have the property that they are grammatically identical to this word, whereas here we have a more grammatical divergence. So overall, they find if they do this modification, but that's also more costly because we have now 4 times more parameters. If we do that modification, we get embeddings that are more grammatical in nature, even though they of course also preserve semantic relatedness, right? So you see that breaking and putting, turning, these are also semantically related words. And what people find is that if we have such embeddings, then they work slightly better for some tasks, like tasks that are more syntactic in nature, such as part of speech tagging or parsing. So you feed in such embeddings to a syntactic task, then you get better results in general. And this is the paper here from 2015. A similar idea, a similar idea in terms of results, but implemented differently, is the following. What they did is well, you can motivate that differently. One motivation is we want sometimes the word that are in relation with each other are very far away, right? In this example sentence here, I would like to drink a very hot, tall, decaf, half soy, white chocolate mocha. So you see that the words in green, drink mocha, that's actually the essential part, and there's a lot of stuff in between these two words. So now if we would run word2vec, then intuitively this word should be somewhere here because that's an important word for the word drink, whereas tall is not a very important word that makes up the meaning of drink, right? So this word should be here, but it's not because per accident there's a lot of stuff in between, and with word2vec we have this window, right? We fix it to some number 3, and then mocha would fall out of this window. So what can we do to address this? Well, we do dependency parsing, and you already know what dependency parsing is, right? We had a whole lecture on that. Here's a one slide recapitulation of dependency parsing. Basically, we want to outline the grammatical structure of the sentence by putting arrows between two words if they stand in a dependency relation. And if we do that, we could, for example, disambiguate whether the scientists study whales from space, or whether it's from space that they study whales, or whether they study whales that come from space, right? So in this case down here, the whales are from outer space, and in this case they study the whales and they study them from space, okay? So dependency parsing can help resolve ambiguities. And now how would we do that? Well, we have our sentence here. We apply the Stanford dependency parser. There are other dependency parsers out there, so such tools exist. They have been trained. They are also deep learning models. You know that, you have seen that in the lecture. So we plug it into some parser, and the parser will give us all the important information. For example, the parser may say that drink at position 5, 1, 2, 3, 1, 2, 3, 4, 5 is, or like mocha at position 14 is the object of drink. And then also here it's like it says what kind of object, direct object or something. So we get this information. And then what they do is very simple. The word2vec model has the following property. It predicts neighbors, and the neighbors are given by a linear window. And this linear window just means all the words surrounding the current word, like in the linear arrangements of words in a sentence. And so the neighborhood that is being predicted, the context that is being predicted, is totally determined by the linear arrangement of words in a sentence. In contrast, with we can also replace this context not to be a linear context surrounding the current word, but being determined by the dependency structure. And now we say that not, like, to, and very are the context of drink, but mocha is in the context of drink, right? So mocha is in the context of drink, and maybe also like, right? So like drink mocha. So this is the direct context of the word drink. So we exchange the context, we redefine the context not to be the window surrounding the word, but being given by this dependency structure. Yeah, so that's exactly that. And then once they apply this model, so if we have the word like, the context would be I, which is the subject, and would, which is the auxiliary verb, and drink, but that's a complement and grammatical complement of the word like. And for drink, the context would be I drink mocha, and then maybe also other things like or something. And if you see these inversion signs here, it means whether the word is the head or whether it is the modifier, right? So that is all. So whether drink is in this position, whether drink is the first argument or the second argument. So these are the contexts that they are predicting. So they change the definition of the context, and they find a similar situation for like for the structured skip-gram models, that now what changes is the nearest neighbors of the words. And we can look, for example, similar as before, we can look at the SIBO model, for example, with a context window of 5 and a context window of 2. We find that the nearest neighbor of Turing are like non-deterministic, in different writing forms, computability, deterministic, finite state. Whereas with Turing, whereas with the dependency-based model that exchanges the window-based context with a context that depends on the dependency structure of the sentence, we find words like Pauling, hoteling, hating, lessing, hemming. Now you can say, why do they all end with ing? That looks similar to the other case with putting and breaking. And the authors say that's a little bit by chance. And down the list, if we would check for more nearest neighbors, then there would also be other scientists that do not end with ing. But the important thing is these are all scientists. So the nearest neighbors are all scientists. And then how they phrase that is Word2Vec finds words that associate with other words, while these dependency-based embeddings finds words that behave the same way. And the difference is functional similarity. So these words have the same function. They're all scientists, which means that they can function as subjects. A scientist is doing something. Scientist researches elephants. And they can also be objects. Whereas Word2Vec captures more domain similarity. So which words are surrounding, which tend to surround the word Turing, right? Such as a non-deterministic Turing machine. And again, we have the same situation here. What has been the typical finding is that these dependency-based embeddings, they work better with tasks that are more structural in nature, that are more grammatical in nature, that have less to do with semantics, but more with syntax and grammar. And of course, the important thing is, so now we have seen a couple of embeddings, syntactically based embeddings, semantically based embeddings, bilingual embeddings, etc. What are you going to do if you look for your own embedding model in your own language? You should always check out the latest state of the art by just Googling, right? So what we present to you in lecture here is not always the state of the art, because the state of the art is updating very quickly. So if you want to have embeddings for your task, Google them, or for your language, also for Turkish, Russian, German, etc. you can Google your embeddings, with the only exception being that nowadays this big diversity has a little bit been reduced, because most people are using the bird embeddings and maybe the multilingual bird embeddings also.